pages 16 to 23. Please make sure you've watched these videos before watching this, because it kind of all brings it together. They're all posted on our page and they're there for you. Okay, for starters, we're on page 16. We just got to know that tropical regions on Earth absorb heat, while latitudes greater than 40 degrees north and south have a heat deficit or loss. So towards the equator, the Earth is absorbing more heat than it's shooting back out into space, and the opposite's true closer to the poles. Okay, so this heat imbalance is responsible for most of our weather and climate. Now, oceans are able to absorb 90% of the solar energy striking them for the following reasons. Water covers 70% of the planet. Water has low albedo, so it doesn't reflect that much. It actually absorbs a lot of the energy from the sun. Water has a large specific heat capacity, as well as large heats of vaporization and fusion. And water is liquid, and the heated water on the surface mixes with the colder water below. Moving on to page 17, we're going to say, I want to just get these ideas into your brain, that we have a big guy called the Gulf Stream, and it's a large surface current that starts in the warm, shallow seas of the Caribbean. From there, it moves north along the east coast of the US and Canada. Then it travels across the Atlantic Ocean, bringing warm, moist air to Great Britain. When it gets there, it's called the North Atlantic Drift. The Gulf Stream is part of a global ocean current called the thermohaline circulation. It looks like this big red line on your leftmost, on both pictures here. And this has a big effect on the world, and there's so much water in the world. So water is amazing and has a huge effect on our lives on a global level. The videos talked about El Nino and La Nina. This is in your notes for you to reflect on if you need to. Again, it's a disruption of the ocean atmosphere system in the tropical Pacific that typically occurs every 3 to 7 years. In your notes, you have some strong notes on El Nino, and recognizing that it has negative effects of flood, drought, famine can result, but there's also hypothetically positive effects of reducing intensity and number of hurricanes in the Atlantic and reducing the number of tornadoes in so-called Canada and the US. So that hits home. This directly affects where we live, you know? La Nina is the exact opposite. And so cool water from the ocean depths near the west coast of South America rise, warm, and flow westward across the Pacific Ocean, and it produces wetter conditions than normal. So in North America, cold air from Alaska moves southward across Western Canada and the US. Again, this is all in your videos. If you didn't watch them, just pause right now and go watch them. Okay, a few more notes in your booklet here. We have what are called westerlies, and that's wind that comes from the west, and that's the patterns we have here in Canada. When someone says prevailing westerlies, that's wind that comes from the west most of the time. Low pressure system, again in those videos, is when as warm air expands, it becomes less dense and rises from the surface. And then in high pressure zones, that's cold air contracting, becoming more dense and descending towards the surface. So in between those cells, in some places we have warm air going up, and as it goes up, it loses moisture, and so that we'll tend to have rain in those areas. And I'm looking at this diagram in the bottom right here, and as air comes together, and starts to descend, it actually creates more dry areas and what we call a high pressure zone, because it's creating a lot of pressure on the surface there. Okay, we have something called convection currents, and the videos covered this, but as land and ocean near the equator is heated by the sun's radiation, it heats the air. That air becomes less dense and rises, and that creates that low pressure zone. As the air rises, it moves towards the Earth's poles and begins to cool. As it cools, it becomes more dense and descends, creating a high pressure zone. Now this picture in your bottom left, that's a super simplified picture. It's actually a lot more complicated than that, as you saw in the video. Boom. So in reality, we actually have this system that almost looks like a little bit of gears. So it's not just one whole system that goes from the equator to the poles. It's actually kind of three in each hemisphere that we're looking at. So a big thing to think about here is that the surface area of the Earth is far larger at the equator than at the poles. So because of this, the warm air traveling towards the poles cools before it actually even gets there, and it becomes more dense and then descends. So air descends at 3 separate latitudes in each hemisphere. So we're talking 30 degrees, 60 degrees in the north and south poles. So that's why we have these three they almost look like gears, and how, if you look at how they connect, they work just like gears too, in a clock or whatever, in a car if you're in mechanics class. So when that warm air from the equator rises and it travels northward, for example, as it descends with the Hadley cell, it's meeting up with that darker blue cell, the Ferrel cell, and air from both of those are going down together, down towards the 30th. Okay, so again, and we're on page 19 now. The diameter of the equator is far larger than that at the poles. Because of this, the equator is traveling far faster as the Earth spins than the poles do. So just imagine you're on one of those old school merry-go-rounds at a playground. If you're on the edge of it, you're going really fast. But then if you move towards the center of it, you're not moving so fast. That's all we're trying to say here. And with that, from the video, I won't make you read through it, but it's in your notes. We have a little explanation here, that northeast trade wind, which is right at the equator. In your notes, I also have pretty good word explanation of the southeast trade winds. So that's in there for you if you want to look through it. Again, I'd recommend watching the video again if you don't really understand those. And you don't have to understand those deeply. Just know that they exist and know that it's a super interesting, complex system. We talked about prevailing westerlies, so that's at about the 60th. And then we also have polar easterlies, which were talked about in those videos. So this is in your notes on page 20 if you want to review it, or if you need to access that. But again, I highly recommend watching the videos, because just having that visual makes it so much easier. Page 20 again, we have some diagrams here similar to those videos, and we can kind of see here just those cells that I'm talking about again, and how they work almost like a system of gears. But then when we mix it with the Coriolis effect, it ends up with these interesting winds going across the Earth, and that they're consistent, and that they create this pattern that we can recognize. And just like when we talk about the trade winds, how sailors recognize that those exist and it's a consistent pattern, they've actually affected how humans have adapted to the world on this global level of trade. So interesting. Okay, so the Coriolis effect applies to any body moving on or above the Earth's surface, so air, but also ocean currents. And oceans also move with the same convection currents as the air, allowing all of the oceans on the planet to mix properly. So again, all of this affecting our climate in a huge way. We talked about jet streams in the videos, but jet streams are, they're currents of extremely fast-moving air, about 10 to 15 kilometers up. And we're on page 21 right now in your booklet. We're just running through your notes here. So jet streams form at the boundaries of those core of where that cold and warm air meet. In the winter, when the temperature difference between cold and warm air masses is greatest, the jet streams usually larger, and they travel much faster than they do in the summer. We're on page 21 now. The polar jet stream effect in Canada is formed between the prevailing westerlies and the polar easterlies. So if you look on this diagram, we can kind of look at it right here, and we see that, and we can, if looking at the map, that kind of hits exactly where we are, right? So the combination of convection and the Coriolis effect intensifies the speed of the air and eventually creates this jet stream. Intense winds within the jet stream influence precipitation and thunderstorms. So what we're doing is we're kind of digging in deep right now, and we're seeing like, oh, there's a reason this stuff happens around us, and there's patterns that are discoverable. I think that's a big lesson in life. There's patterns that are discoverable, And whether you're in social studies, in science, in math, in English class, in a different language class, we'll start to notice patterns. So watch for those patterns. When we're considering how oceans and mountains influence climate, we want to consider two properties of air. And first one being when moist air cools, it can't hold as much water, and that water condenses and might fall as precipitation or rain. Warm air rises and cooler air moves in to replace it, and this produces that current moving air, or convection, if you will. On page 22 here, a few more ideas that I want everyone to get in their heads is we have what's called a sea breeze, and that's as the sun rises in the morning, it heats the land and the water, but the land warms up faster than the water because it has the lower specific heat capacity. It takes less energy to heat it up. So the air above the land warms by conduction, again, that heat radiating out of the ground into the air warms the air up, and that air rises. So the warm air travels over the water and cools, descending towards the surface of the water, and that creates one of them flows again. So that was a sea breeze. We have a land breeze as well, and I'll show you a picture in just a second in case you're a kind of person like me who needs pictures. So what we call a land breeze happens as the sun sets at night, and the water holds on to the heat longer than the land because it has a larger specific heat capacity. So it's the exact opposite of a sea breeze. Now the air above the sea warms by conduction again. That heat is radiating off the water, it's heating up the air, and then that air rises and warm air travels over land and cools, descending towards the surface of the land, and then the cool air, which is now wind, moves towards the sea to fill in where the warm air that's risen. So let's take a look at this picture. It might make a little bit of sense for people who find it hard to follow words, which I certainly do. So we have in the morning, in this diagram, we have the land heating up, so that air gets warm, it starts to rise, and it travels out over the water, and as it cools down, it drops down, and then that cold air is replacing that air that was over the land, and it ends up having this breeze that's going inland. At night, we're talking about the exact opposite. We have this air being warmed by the water that's warm for longer than the land is, and it's going up and it's creating the exact opposite direction of a breeze. So a land breeze, it creates this feeling of the breeze leaving the land and going out to the ocean. So it's coming from the land, we call it a land breeze. With the sea breeze, it's the exact opposite. It feels like this wind is coming from the sea. Okay. So the proximity to water can have two effects. With climate, the temperature is relatively consistent throughout the year. And in terms of moisture, the air next to the water is much more moist than inland areas. So proximity, that's just a fancy word for meaning if something's close to it. So for example, if I live in Vancouver, the temperature there will be relatively consistent throughout the year as compared to Calgary, because Vancouver is close to the ocean. And then also it'll be much more moist there. I know, for example, when I've lived in Vancouver, when I come back to Calgary, my lips get all cracky and dry, like right away. And it lasts about a week or two just until I get used to the dryness of the air here. Okay. So one last big fancy term for you is orographic precipitation. Now, looking at this little map here, what we see is when the warm, moist air blows onto land and meets mountains, so warm, moist air blowing onto land from the ocean, what we call orographic precipitation occurs in the form of rain and snow. So again, talking about Vancouver here, warm air comes off the ocean, hits the mountains, and as it hits the mountains, it drops a whole bunch of rain there. So that's what we call orographic precipitation on kind of the ocean side of the mountains. Now then on the other side of the mountains, we have what's called the rain shadow. And when warm, moist air forms precipitation on one side of the mountains, it loses all that moisture over Vancouver, and then that same air comes over the other side, and it has no moisture left, so it can't create much rain, and this is known as the rain shadow. So there we go, dear friends. We